Now let's move on to the fruit model law. Fruit model law says that the fruit number of the model should be equal to the fruit number of the prototype. That means V by root GL of the model should be equal to the V by root GL of the prototype, or VM divided by root of GM into LM should be equal to VP divided by square root of GP into LP. Here we know that GM is equal to GP because acceleration due to gravity is constant for both model and prototype. So we can write it as Vm divided by root Lm should be equal to Vp divided by root Lp. And on rearranging we will get Vm divided by Vp is equal to 1 divided by square root of Lm by Lp. But here we know that Lp divided by Lm is equal to Lr, that you have seen during the geometric similarity, that is the ratio in between the length of the prototype divided by length of the model should be equal to Lr, that is the scale ratio for length. So we can write Vp by Vm is equal to square root of Lr, and it is called as the scale ratio for velocity, that is the velocity of the prototype divided by velocity of the model. So we can say that the scale ratio for velocity should be equal to square root of Lr. So in this way, using the Freud model law, we can derive the scale ratio for different physical quantities, just like the scale ratio for time, scale ratio for discharge, scale ratio for force, etc. Now let us derive them one by one. First of all, we have already did the scale ratios for length and scale ratios for velocity, and let's move on to the scale ratios for time. So we know time is equal to length divided by velocity. Scale ratio for time period can be written as TR, which is equal to the time period of prototype divided by time period of the model, and it can be written as L by V of the prototype divided by L by V of the model. On rearranging, we will get LP divided by LM into VM divided by VP. Here we know that length of the prototype divided by length of the model is equal to the scale ratio for length, and velocity of the model divided by velocity of the prototype is the reciprocal of the scale ratio for velocity. On substituting these values, we will get TR is equal to LR divided by root LR, that means square root of LR. So we got that the scale ratio for time is equal to square root of LR. Now moving on to the scale ratio for acceleration. Acceleration can be written as velocity divided by time. So the scale ratio for acceleration should be equal to acceleration of the prototype divided by acceleration of the model. That means velocity by time of the prototype divided by velocity by time of the model. And it can be written as velocity of prototype divided by time of the prototype into time of the model divided by velocity of the model. And on substituting the scale ratios, we will get a square root of LR divided by square root of LR, that means 1. So the scale ratio for acceleration is always 1. And now let us derive the scale ratio for discharge. We know discharge Q is equal to AV, where A is the area and V is the velocity. Now substitute the dimensions. A is equal to L square and V is equal to L by T. So we can write it as L cube divided by T. Now go for the scale ratio for discharge. It is equal to the discharge of the prototype divided by discharge of the model. Or it can be written as L cube divided by T of the prototype divided by L cube divided by T of the model. On substituting and rearranging, you will get a scale ratio for length the whole cube into the reciprocal of the scale ratio for square root of the length. So it can be written as LR cube into 1 divided by square root of LR, that is equal to LR raised to 2.5. Now moving on to the scale ratio for force. We know force can be written as mass into acceleration, that means ml t raised to minus 2. But here we should substitute for m and t. We know mass is equal to volume into density, and also time is equal to length divided by velocity. On substituting these values, we will get a force is equal to rho L square V square, where rho is the density, L is the length, and V is the velocity. Now you go for the scale ratio for force, Fr, which is equal to force at the prototype divided by force at the model, and it will be equal to rho p into Lp square into Vp square divided by rho m into Lm square into Vm square. But here we know that the density of the medium at which the prototype exists should be equal to the density of the medium at which the model is existing. So rho p becomes equal to rho m. So rho P by rho M should be 1, and the scale ratio for force become LP divided by LM the whole square into VP divided by VM the whole square. On substituting the values, we will get LR square into square root of LR the whole square, and it will become LR cube. That means the scale ratio for force is equal to the cube of the scale ratio for length. Now let's move on to the scale ratio for pressure. Pressure can be written as force divided by area, which will be equal to rho L square V square divided by L square, and it will become rho V square. So the scale ratio for pressure will be equal to the pressure at the prototype divided by the pressure at the model. That means rho V square at the prototype divided by rho V square at the model. On substituting, we will get here also rho P is equal to rho M. That means the density of the fluid will be the same for both the prototype and model. So we can write the scale ratio for pressure is equal to velocity of the prototype divided by velocity of the model the whole square. That means square root of LR the whole square, that is LR. So we can say that the scale ratio for pressure is equal to LR. Now move on to the scale ratio for work. You know, work is equal to force into displacement. So the scale ratio for work WR should be equal to the work on the prototype divided by work on the model. That means FL on the prototype divided by FL on the model. Now you can do it in another way also. That means just multiply the scale ratio for force and scale ratio for length. You will get the scale ratio for work done. That means FR into LR. You will get LR cube into LR. That means LR raised to 4. So the scale ratio for work should be equal to LR raised to 4. Now you remember one more thing. The scale ratio for work should be equal to the scale ratio for energy, torque, etc. Because all work, energy, torque, etc. are having the same dimensions, m l raised to 2 and t raised to minus 2. So let's move on to the scale ratio for power. We know power is equal to work per unit time. So what will be the scale ratio for power? It will be the scale ratio for work divided by scale ratio for time. That means LR raised to 4 divided by root LR, and it becomes LR raised to 3.5. So the scale ratio for power is equal to LR raised to 3.5. In this way, for university, they will ask to derive each scale ratio, and each of these scale ratio contains some 1 mark or 1.5 mark. Now we are moving on to the last concept in the 6th module. It is the types of models. Model can be classified into distorted models and undistorted models. In undistorted models, the ratios will be same in both horizontal axis and vertical axis. But in distorted models, the ratios in the horizontal axis is not equal to the ratios in the vertical axis. Now it's mainly used to reduce the economy. Here in university, they will ask theory questions to differentiate between the distorted models and undistorted models, or they will ask to write the advantages of the distorted models. Now that's all about this module 6. Thank you all. Have a nice day.